Large language models can pass the bar exam, diagnose rare medical conditions, and generate complex software architecture in seconds. Yet when you ask that exact same advanced model a seemingly trivial logic question, the cognitive bridge completely collapses. It might struggle to deduce that if person A is the sibling of person B, then person B is the sibling of person A. For years, the AI industry has documented these reasoning failures as isolated quirks. Without a unified theory, these observations remain anecdotal and fragmented, often addressed only through trial and error prompting. To build reliable systems, we must move past these individual case studies. We have to map erratic behavioral patterns back to their mechanistic causes in the model's architecture. Solving hallucination requires an architectural shift, beginning with a systematic categorization of how these models actually fail. This matrix represents the first comprehensive survey mapping LLM reasoning failures across two distinct axes. The vertical axis divides tasks into informal, formal, and embodied reasoning. The horizontal axis distinguishes the failure's nature, from fundamental flaws to application-specific limitations and sensitivities to minor variations. Organizing the field this way provides a framework for identifying specific mechanical bottlenecks that current benchmarks often miss. By isolating a specific failure within this grid, we can begin to reverse engineer the specific training dynamic or architectural constraint responsible for the breakdown. We start in the top row, informal reasoning. This covers the model's attempt to emulate intuitive judgments, core cognitive skills, and everyday decision-making. When navigating complex, multi-step tasks in this domain, the model's working memory acts as a primary site for fundamental failure. The underlying issue lies mechanically in the transformer's self-attention module. As a context window fills up, the mechanism disperses its focus. This creates proactive interference. The model overwrites or ignores earlier contextual information in favor of the most recent tokens it processed. Human working memory operates differently, prioritizing goal-oriented retention, regardless of when the information was first introduced. Without that stable internal workspace, an LLM's memory is a decaying statistical window, highly vulnerable to interference as the prompt length increases. Within informal reasoning, we also find limitations in social deduction. Models are typically evaluated using theory of mind tests, like false belief tests, designed to measure an understanding of human mental states. Advanced models initially appear to pass these evaluations, suggesting they harbor a latent internal model of human psychology. But apply a logic-preserving, minor semantic perturbation to the prompt, swapping a single harmless word, and the model's accuracy drops abruptly to zero. This instability indicates the model is relying on surface-level linguistic patterns from its training data, rather than performing genuine social deduction. In these contexts, passing a standard benchmark does not prove the model possesses the underlying cognitive capability being tested. Moving to the middle row of taxonomy, we encounter formal reasoning, which requires the rule-based manipulation of mathematics, code, and symbols. Here, autoregressive architectures exhibit a universal fundamental failure known as the reversal curse. Take a factual relationship. If a model is trained heavily on the premise that Tom Cruise's mother is Mary Lee South, it will struggle to deduce that Mary Lee South's son is Tom Cruise. This failure is tied directly to the model's training objective, next token prediction. Causal masking prevents the network from predicting antecedent words, embedding a strict structural asymmetry into the model's weights. Because unidirectional prediction does not naturally manifest bidirectional logic, this failure persists regardless of the amount of compute or data used during training. This structural asymmetry undermines the reliance on static benchmarks to validate formal reasoning. When a model faces a logic-preserving transformation, such as reordering the multiple choice options, the final answer often changes. This represents order bias. The transformer's positional encoding and causal masking anchor its logic to the physical position of the text rather than the logical structure of the problem. These shifts reveal training data contamination, where a model has overfitted to the specific formatting of public datasets. High benchmark scores frequently measure a model's ability to recognize a formatting template, rather than its capacity to reason through a novel problem. In the bottom row of our taxonomy, we find embodied reasoning, the ability to interpret spatial relationships, predict physical dynamics, and execute 3D planning. The core limitation here is physical grounding. Large language models learn from disembodied text strings. They possess no sensory connection to the physical world. When these models act as agents, this lack of grounding results in affordance errors. A model may command a physical body to move through a solid object because it cannot predict the physical consequence of the action. Furthermore, autoregressive generation without a spatial memory frequently traps these agents in illogical, repeating action loops during multi-step execution. Semantic comprehension of physical terminology does not translate into actionable physical intuition. Reviewing the complete taxonomy chart reveals that these errors are not random. Whether they appear in cognitive, logical, or physical tasks, these failures trace back to 3 shared architectural limitations. First, the mechanical dilution of self-attention, which degrades context retention and working memory. Second, the unidirectional nature of next token prediction, which prevents symmetrical logic. And third, the absence of an internal world model, preventing true spatial intelligence. These logic breaks are the predictable, inevitable outcomes of the current transformer blueprint. Mitigations like chain of thought prompting or RLHF only address the behavioral output of the model. They do not change the underlying architectural constraints. The scaling hypothesis argues that adding parameters and data will eventually bridge these gaps. But scaling a flawed architecture yields larger, more confidently articulated failures. True progress requires structural shifts toward non-auto-regressive planning modules and integrated physical simulators. Research must move beyond the assumption of latent human reasoning in LLMs and focus on building systems with verifiable logical depth. To build models that genuinely reason, we must move toward architectures that support symmetrical logic and grounded physical understanding.